Hello. So thank you all for joining us. So my name is Sarah, and I'm joined by Salvador. And we are both research scientists at Epic Games. So today we're going to be talking you through xADA, Expressive Audio-Driven Animation for MetaHumans. And this is technology that's been part of MetaHuman Animator since 5.5. But with the 5.6 release, we've introduced some new updates, including audio-driven head motion, a greater control of facial expression, and also our streaming solution. So first off, what do we mean by audio-driven animation? So we are defining audio-driven animation as the system for predicting lip sync, facial expression, and head motion of a character directly from the audio speech. So speech goes in, animation comes out. And why are we doing this? What is our motivation here? So as you're all very aware, facial animation is a key component of character animation, but it is incredibly difficult to do it very well. So the problem is, as humans, we are so used to seeing how humans' faces move, and we're really tuned into the subtleties of expression, like the nuance of articulation. And so if facial animation is not 100% accurate, we really do notice, and it can be quite distracting. And this is especially challenging as we approach photorealism, as we are with MetaHuman. Now, because audio-driven animation, it's a machine learning approach, we are training our models on real examples of how real faces move during speech. It does give us the potential to get much closer to facial realism, to human realism, much more easily. So secondly, facial animation, it's a laborious process. So classically, facial animation has been done by hand, and this is incredibly time-consuming. More recently, facial performance capture is becoming more popular. This is also not a particularly fast process, especially if we start working with thousands of audio samples, for instance. So in contrast, audio-driven animation is fast. And it really does provide us with the potential for really speeding up the animation pipeline, because it gives us the ability to generate either the animation or at least a starting point for an animator incredibly quickly with just a few clicks. And then finally, hand animation, performance capture, these are really great for generating offline content where we know all of our speech content ahead of time. But audio-driven animation, it opens up the opportunity for interaction. And this is because we can generate animation on the fly. And this is really, so as audio streams in, we can stream out animation. And this is really essential for things like AI characters, or really any type of interaction in the metaverse. And so in this talk today, Salvador will be talking through our streaming real-time solution in the second part of the talk. So today, first, I'm going to be going through the research behind our audio-driven animation in MetaHuman Animator. I'll be talking you through our training data, the model that we train and how we train it, and then I'll give a very quick demonstration of how you can use this in the engine. And then I'll hand over to Salvador, who'll talk you through the streaming solution. Okay, so we need to train our model on examples of how human faces and heads move during speech. There are some very small number of existing speech and 3D animation datasets that we can use for this, but all of them are very limited. So some are limited in terms of their size, others are limited in terms of their expressivity, and none of them contain any examples of laughter, singing, nonverbal sounds, and none of them have any head motion or tongue motion in them. So for these reasons, we decided to capture our own data. And we spent quite a lot of time designing the data before we set out to capture it. So we're probably all aware here that machine learning models, they're really only as good as the data from which they've been trained, both in terms of quality and in terms of diversity. So we want to make sure that we collect all the different types of behaviors that we want our model to be able to animate to. So first up, of course, we want our model to have really high quality, really articulate lip sync. And for this reason, we collect a few hundred phonetically balanced sentences taken from the Harvard corpus, which is cited below. By phonetically balanced, I mean they contain a diverse array of different phonemes or speech sounds in many different contexts. So they've got a good coverage of co-articulation, which our model needs to learn from. An example of one of these sentences is, the birch canoe slid on the smooth planks. And we collect performances of these sentences in a very neutral style. Having said that, we do also want to capture expression and really emotional speech too. So we designed a list of 21 different emotional categories, and we took this list from different academic sources. For each of these 21 emotions, we scripted 3 or 4 different sentences, and these were designed to really get our actor to incite those emotions, or to perform those emotions. And for each of these sentences, we collected performances of them at varying intensities, from low intensity up to exaggerated intensity. So an example of a surprise sentence might be, "You're here. I didn't know you were coming back." Now, the problem with these first 2 categories is that when we ask our actor to perform them, we provide the prompt for them on the screen, and they read the prompt from the screen. So because of this, we are not collecting natural blinking or natural head motion. So what we also do is we include several sessions of unscripted dyadic conversation. This is essentially a conversation between our actor on stage and somebody else. And although this is unscripted, we do provide some prompts just to keep the conversation flowing if necessary. So one of these prompts might be, where would you go on vacation if you had no budget? And in these sessions, this means we're capturing, because it's completely unscripted and free-flowing, we're capturing natural blinks, natural head motions, and all these spontaneous expressions and really interesting things that come from real-life interaction. And finally, we also want to be able to animate non-verbal sounds. So as humans, we make all these different noises and sounds that they're not directly related to verbal communication, but we make them very frequently. Things like coughs or clearing our throat or sniffs or laughter even, tuts, all of these things. They're all very interesting and we want to be able to animate these. So we put together a list of the commonly used ones, and we also capture repetitions of each of these. So for each of these categories, we capture the synchronized audio, face, and body motion from 10 actors. We collect audio from a microphone that's attached to our actor's chest, and we capture that at a sampling rate of 44 kilohertz. We capture the facial performance from this stereo HMC, so we're capturing a top view and a lower view of the face simultaneously. We capture the body with this 24-camera motion capture system at 100 frames per second. So next, I'll talk you through how we process the face and the body data. So let's start with the face. So for each of our actors, we first create a personalized MetaHuman facial control rig. And then what we do is we solve their facial performance from their video to their personalized control rig. And we do all this using the fantastic tooling that's available in MetaHuman Animator. And this is available for anyone to use. So let me show you some results of this facial solve.
With tenure, Susie'd have all the more leisure for yachting, but her publications are no good.
He ripped down the cellophane carefully and laid his 3 dogs on the tinfoil.
So we did this for all of the actors in our data set, so here are some more examples. And this gives us a really nice representation of how the faces are moving during the speech. So the MetaHuman facial control rig has over 160 controls on it, but we don't use them all. We're kind of interested in keeping the broad facial motion. So for this, we keep the primary controls and we remove the tweakers. We also, at this stage, remove the eye gaze controls because, as I previously mentioned, most of our data is from read performances, read prompts from a screen. So at this stage, we're not interested in modeling eye gaze. So after this step, this results in a reduced set of 81 controls that encode the facial performance. This means we end up with this 81-dimensional vector for every frame in our video, in our captured video. And this representation is essentially what we want our model to output. This is the representation of the model output. So I'm just going to talk about the tongue quickly, because the tongue is something that MetaHuman Animator does not solve for. When the tongue is visible, it's actually incredibly important to our perception of speech, and it really aids kind of speech interpretability and understanding. However, most of the time, the tongue is occluded by the teeth and the tongue and the lips, and you can't actually see it. So it's almost impossible to track the tongue directly from the video. So instead, we leveraged this existing tongue mocap dataset called IMT 2022, or 22. This was actually captured as a collaboration between Epic Games and Haskins Lab at Yale a few years ago now. And it contains approximately 2.5 hours of a single actor, or my boss, saying phonetically balanced sentences. And it contains the speech together with the tongue mocap data. The tongue mocap data was collected using an electromagnetic articulograph, or an EMA device. And it collected the motion of 10 sensors positioned on the tongue, the lips, and the jaw. And you can see the lip ones on that image there on the right. And then using both the position and the orientation of these sensors, we solved these to the MetaHuman tongue controls, as you can see down there on the right. And I should say that this data set is actually available for anyone to use. It has been released. So the way that we use this data set is to generate synthetic tongue animation for our captured data. So the first step in this process is that we train this speech-to-tongue model, which is trained completely on the IMT22 dataset. And it learns to map from the audio of the IMT22 dataset to the tongue rig controls of this dataset. And then once this has been trained, we simply input the audio from our captured data, and this gives us a prediction of how the tongue's moving for that captured data. And we merge these controls with the solved facial controls. Okay, so next I'll talk about the body data. So let me just play this video. So the first thing that we did is we retargeted our captured mocap to the MetaHuman skeleton, as you can see on the left. We were careful to choose the skeleton preset that best matched the proportions of our actor in terms of their height and their build. Now we have parametric bodies, maybe this could be improved even further. But actually, we are only interested in this project in adding on like a little bit of prosody-related head motion. So we only retain the head motion for this project, as you can see on the right. We are representing head motion with the motion of the last 4 bones along the kinematic chain to the head. So this includes spine 5, neck 01, neck 02, and head. Let me just play this one more time. And we represent these joints as 6D rotations. So this representation is becoming quite popular in machine learning because it has some really nice properties. So they don't suffer from gimbal lock, like Euler angles, and they are continuous through 0 as well. We also keep like the relative translation of the pelvis. You see there's some lateral motion in that video on the right there because it adds some more richness to the animation. Okay, so after all of those processing steps, this is what some of our training samples looks like.
I can't believe how amazing today has been. Everything is falling into place perfectly.
I know I let you down, and I feel so terrible about it. I just hope I can find a way to make it right.
So yeah, we've got a nice mixture of things there. Okay, so next I'll talk about the machine learning model, architecture, and a few details about how we train it. So this is our model. If we zoom out a little bit, you can see at a very high level, the audio is given as input on the left. And the 2 outputs of our model are the head motion, as you can see on the right. And then this is in the 6D representation that I previously mentioned. And the facial animation, which is on a MetaHuman. This model is incredibly modular. So first, I'm going to be talking you through this module here, which is responsible for generating the facial animation. Then I'll touch upon this module, which generates the head motion. And then finally, I won't talk through this one today, but we have this final module, which generates additive blinks. And we refer to this entire model as xADA, which stands for Expressive Audio-Driven Animation. OK, so I'll start off with describing the facial animation module. So for this, we take a transfer learning approach. This means that we take a model that was trained for one task and then use it for a related but different task. So in our case, we take the encoder from OpenAI's Whisper model, and this was trained for speech recognition, and we apply it to our facial animation task. And the reason that we do this is because the Whisper model has been trained on hundreds of thousands of hours of audio speech. And in this speech data set, it contains diversity in terms of like speaker, so speaking style, language, it contains loads of different languages, environmental conditions and therefore noise conditions, all of these things. And this means that it's incredibly robust at extracting speech-related content from the audio, regardless of any of these factors. And this means that we can also train our facial animation decoder on much less data because Whisper is doing so much of the heavy lifting for us in terms of audio signal processing. So what we do is we use the encoder from the Whisper model to extract features, audio features from our audio signal, and then we train up a facial animation decoder which converts these features into facial animation on a MetaHuman. We also want to control somewhat for the speaking style and also the emotion on the generated animation. So we also train up a few extra layers to embed both the speaker ID and the emotion ID, and then we use these as an additional inputs to the facial animation decoder. So some technical details here. Our facial animation decoder is trained as a 7-layer, 512-unit, bidirectional GRU model, which is a gated recurrent unit model. We train it from scratch on Epic's data. We train it on overlapping 5-second samples with a stride of 1 frame. And this model took approximately 2 to 3 days to train, but this is incredibly hardware dependent. I'm just giving you an example or an indication of the scale of the problem. And we train it in a supervised manner. We simply minimize the mean squared error loss between the predicted output and our captured performance data. So let me show you a result of this model.
At one end stood a great fireplace, in which a blue log was blazing with a blue flame, and over the fire hung 4 kettles in a row, all bubbling and steaming at a great rate.
So that one was that's very neutral, but as I previously mentioned, we can control for the emotion on the face. So let me show you a happy sample.
"I think I must show you my patchwork girl," said Margolot, laughing at the boy's astonishment, "for she is rather difficult to explain."
And the model is trained with 21 different emotion categories, and this is all of them.
We may be stopped. The fact may be put to us in general terms, which is one way of attenuating it. We may be told that all trades, professions, it may be added, all the accidents of the social hierarchy and all forms of intelligence have their own slang.
Now, the problem with this model is that it requires a speaker ID and an emotion ID to be given as input kind of manually for it to run. But there are times when we might want to run this model completely automatically. So the question is, how can we run this model fully automatically? Say, for example, we do have like 1,000 audio clips that we want to process, and each audio clip has like a different emotion, or it changes throughout the sequence. We may want to automatically detect the emotion from that audio sequence rather than having to manually input it. So we want this model to run fully automatically. For the speaker side of things, what we actually end up doing is taking the mean vector from the speaker embedding layers and using that. And actually, all the examples in this talk use that as the speaker embedding. This kind of gives us the most generic speaking style from all of the actors that we captured and works best across most of the rigs that we've tried. But for the emotion, it's a bit more tricky. So what we do is we introduce an emotion classifier. And this is responsible for detecting the emotion from the voice. The input to the emotion classifier is the Whisper features. And the output is like the emotion probability. So the probability distribution over the 21 different emotion categories. And the output to the emotion classifier is used as input to our emotion embedding layers. The emotion classifier is also trained as a bidirectional GRU, this time with 4 layers and 256 units. And the great thing about this framework is that the model can now be run either fully automatically by taking the output from the emotion classifier as input to the emotion embedding layers, or a user can override this and instead put the user-defined emotion into the emotion embedding layers. So here's another example. This time, the automatic configuration is shown on the top left.
You are now in the only country in the world where wit can make a fortune by selling either a genuine or a false article. In the first case, it receives the welcome of intelligent and talented people. And in the second, fools are always ready to reward it. For silliness is truly a characteristic of the people here, and however wonderful it may appear, silliness is the daughter of wit.
So you may notice that in this example, there is head motion. So that leads me on to the next section. Okay, so when it came to training the head motion model, the question that we posed was, what information actually drives head motion? What inputs does our head motion decoder need to generate the most accurate head motion animation, or head animation? So we set up an experiment where we trained our head motion model on different combinations of input features, including audio, face, speaker, and emotion information. And then, as you can see on the table on the right, we measured the head error over our test set for each of these combinations of features. In the top row, you can see that if we use audio alone, we get an error of 1.03. If we add in the face information, the error decreases. And it continues to decrease as we add in speaker and emotion information. So we can say that all four of these input features contribute positively to head motion. So that is what we use. Before I show you some more results, I just wanted to talk more about our choice of audio encoder, because I mentioned we use the Whisper encoder. I just want to talk through how we use it and why we use it. So on the right there, you can see OpenAI's Whisper model. The left-hand column, like the pink blocks there, that is essentially the encoder part of the model, and the right-hand column is the decoder part of the model. So the encoder part of the model is responsible for converting the audio features into a set of features, and the right-hand part of the model is essentially responsible for turning these into tokens or text. And we're not interested in this part of the model, so we simply remove it. And this leaves us with the encoder only. What this does is it converts our audio into a log-mel spectrogram, passes these through 2 convolution layers and 12 transformer blocks, and it's the output of the final transformer block that we use in our model. And we did compare Whisper against different pre-trained audio encoders that exist, namely WAV2VEC2 from Meta, which is very commonly used for audio-driven animation in academic literature, WAV-LM from Microsoft, and also Hubert from Meta. And you can see in the table below, we report the face animation error and the emotion classifier accuracy in the columns 2 and 3. And we report these for each of the 4 different audio encoders. So Whisper actually performs best in terms of facial animation error. It actually performs second best in terms of emotion classifier accuracy behind WAV-LM. But if we look at that final column, you can see the number of parameters in each model. And actually, all of the other audio encoders share the same underlying architecture. They've just been trained differently. So they all have substantially more parameters than the Whisper encoder does. So this trade-off in emotion classifier accuracy is kind of acceptable for us because it makes the model much more practical. OK, so let me show you some results now. So I need to preface this by saying that none of the audio samples that you see here were used for training the model. They're all from either different data sets or completely held out. I'll start off with some test set examples from our captured data.
Yeah, I recently watched the Baby Reindeer. I think was that Netflix?
Agricultural products are unevenly distributed.
Why do we need bigger and better bombs?
I agree. And I think it's useful to compare against the ground truth as well. So in these next examples, you'll see the ground truth or the captured performance on the left and the prediction from our model on the right.
With tenure, Susie'd have all the more leisure for yachting, but her publications are no good.
From the clips I saw, I thought she didn't have a great hold on what was true and what was not true.
The small boy put the worm on the hook.
And I just want to bring attention to the tongue as well. So on the left, we have the kind of pseudo ground truth tongue motion, and on the right is the prediction from our model.
The small boy put the worm on the hook.
With tenure, Susie'd have all the more leisure for yachting, but her publications are no good.
And all those samples were quite neutral, so I also wanted to show you a few emotional samples. For each of these clips, we also show the probability distribution over the 21 emotions in the top left.
You're here! I didn't know you were coming back. Oh, this is the best surprise.
No manufacturer's taken the initiative in pointing out the costs involved.
So it does a pretty reasonable job there. And although we don't capture any languages other than English in our particular data capture, because we are using the Whisper model, Whisper has been trained on all these different languages. So I think our model fares pretty well over different languages too. Here are some examples.
Et vous serez haïs de tout le monde à cause de mon nom. Mais celui qui persévérera jusqu'à la fin sera sauvé.
Powierzchowność tej udoskonalonej beczki Diogenesa bywa bardzo rozmaitą, bo każdy gatunek wybiera inne materiały i skleja je w inny sposób. Niektóre tylko gatunki należą do niewybrednych i biorą to, co im w chwili potrzeby wpadnie w łapki.
Obviously, I think they look pretty good, but as an English speaker, I welcome feedback from the actual people that speak these languages as to how good they are. And so non-verbal sounds, I previously mentioned that we capture this data, so I wanted to demonstrate what the result of this model is on non-verbal sounds. So we're getting there. And to finish off, I wanted to show you some singing. So all of the samples that you're about to see, we predicted them from the clean vocal track, and then we mixed in the music after.
Jugs of maple, you can throw it on back. Kick it back in front of the fire. Take a load off to your heart's desire. Got a cannon up front, pouring out back. We got home style cooking, and that's a fact. Check the board for what's on tap. We got the best dang slurp on the whole dang map. Pile in the truck and come on down. We got the best food in this whole dang town. Yeah, 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 yeah. Come on down.
Awesome. Cool. So let's it's so difficult not to sing along at this stage, so you're very lucky that I didn't. Okay, so I'm just going to break it out quickly and show you a quick demo of how you can run this in the engine. So to run this, you'll need to enable the MetaHuman animator plugin, and for these particular features, you'll need to be using 5.6. So we've pulled in an audio sample, and we now have a sound wave asset.
When you're less fatigued, things just naturally look brighter.
And there are multiple ways in that you can generate animation from a sound wave asset. The first one is batch processing. So if you right-click this, click on MetaHuman Performance, and then you've got some options there. So you can either generate level sequences, animation sequences, or you can create performance assets. This is great if you have loads of different audio samples. You can just select them all, right-click, and then you can just generate level sequences or animation sequences for all of them with just a few clicks. There's another option, which is the one I'm going to be going through today, and that is via the MetaHuman Performance Editor. So if you go to the MetaHuman menu item and then click on MetaHuman Performance, I guess I'll call this speech clip. And then we open this up. So over here. So in here, if we change the input type to audio, and then we can select our audio sample, so I think that was speech clip. And then we can choose our visualization mesh. So in this case, it has to be Orlando for obvious reasons. And we can simply click process. We have the audio and we have the visualization mesh, and you can see it doing its work. If I make this big, actually. So if I click play now.
When you're less fatigued, things just naturally look brighter.
So this is using the automatic configuration now, where we're automatically detecting the emotion from the voice. We also can override this if we come down to solve overrides down here, and then we can choose which mood we want to animate to. So say if we want to make him angry, we select anger. We can also choose an intensity if we want to lower the intensity or edit that in any way. So once I've chosen anger, let's do some processing again. So let's go back to the beginning. Now he should be more angry.
When you're less fatigued, things just naturally look brighter.
And then from here, we can export.
By that time, perhaps
we can export to level sequence. Save that. Choose our MetaHuman we want to have in our level sequence. I won't export the camera because we have one. And then we should have it. Oh, sorry. Yeah, and here's our level sequence. What I'm going to do is just select our character and point him to our camera. I'll drag our camera in here as well, so it looks nice. And then we have our...
When you're less fatigued, things just naturally look brighter.
So yeah, I mean, obviously he's not speaking in an angry voice, but you get the gist. Okay, cool. So that was the demo. I will now hand back to Salvador to go through our stream model.
Hi. So now I will walk you through the streaming audio-driven animation model. We've been working on this recently, and whenever we're working on this, one of the first questions we always get is, why does it have to be running in real time, or do we need a streaming solution? Well, if we've been looking around here and the industry, we've reached this point where we can beautifully render all these MetaHumans, as the one that you see down there. But not only that, now we are capable of realistically animating these MetaHumans, just as Sarah just showed you, that we're capable of doing with xADA. So with a streaming solution, the thing that we can achieve now is interactive characters, right? And these interactive characters could be either AI-driven, just as we saw with AI Vader in Fortnite. So this would allow NPCs to actually be responsive to the players and have a personality of their own. Or these characters could also be player-driven, right? With a streaming model, we would be able to give the people the power to actually drive their characters and having a more in-depth experience within games. But this doesn't only stop in games, right? This could go into VR experiences or live experiences. And however, this not only stops in video games, this also enables content creation. With this kind of tool, we believe that streamers, VTubers, they would be able to create this amazing, in-depth, high-quality content to bring smiles to everybody. However, bringing this into life isn't easy, because there are a few key constraints that we have to design around. And one of the first key constraints is time. We have a short time budget. What we need to do with this model and this solution is to come up with animation predictions within a frame, right? We cannot take longer than that. We need to deliver one frame of animation that is faster than that. And that will make characters to feel responsive and natural. The second constraint that we have is limited computation. One of the goals here is that we would love this solution to actually be able to run on CPUs and GPUs regardless of whether it's a high-end workstation or something more modest. We are aiming for scalable performance that doesn't bottleneck your system. And the third constraint that we have is a small memory budget. we would like it to be light enough such that it can run on mobile devices or servers at scale without hogging the resources, right? Such that we can deploy it easily within these platforms. So now, to show you how these key constraints come into play, I will describe how the audio is being processed and how it's different between the offline model, or xADA, and the streaming model. So for xADA, you take the full audio into play, right? So here comes xADA. And xADA is capable of seeing the full audio, right, while processing it. So whenever it wants to predict at certain given time, it's capable of looking what's happening in the audio into the future and into the past, right? Once it has determined this is the best frame that I should deliver, it just delivers the full sequence of MetaHuman rig parameters. In contrast, the streaming audio, it has to look at the audio as it comes. So let's take, for example, xADA will only take 1 second of audio at a time, right? So for this second, it can look back and forth, but only within this second, and then determine which is the best animation frame that you have there. Since this is a streaming, we get a little bit more of audio, then we slide xADA, or the streaming model, and make the prediction for the next frame. And this will keep on happening as the streaming comes in from the audio until we get the online solution, right? So now let me show you how this works within the MetaHuman animator. And I'm glad to say that we have the actor here for this performance.
It's also possible to drive the real-time animation from audio only. So in this case, the audio is being picked up by a microphone, fed into UE, and the animation calculated from just that audio. It mostly drives the lower face of the lip sync and the jawline, but also there are some more subtle controls to the upper face.
All right, thank you. So now how does it process like each of these windows? So let's take into consideration this 1 second input window of audio. And the model still consists of Whisper, right? But we do not take the full model because this would actually take a lot of time. So we only take the first few layers. In this particular case is the first 2 convolutional layers, the CNN, plus the first transformer encoder layer. Then we decode those audio features into the actual animation by using a transformer-based model. Same as with xADA, we did not fine-tune whatsoever the Whisper features or the Whisper layers, but we did train the decoder layers. Then, since a transformer is a sequence-to-sequence model, what it will do is actually give you all the animation parameters for that second. But since we're working with streaming, we only select one of those. And that's what we deliver per input window. However, training a tiny model, it usually requires a lot of data when you're trying to compress these models in order that they can generalize. So for this, we distilled xADA by using a teacher-student approach, where xADA would be the teacher and our streaming model, stADA, would be the student. But the epic data that we have consists, for now, of 16 hours and only 10 speakers. So we took another data set, which is the liver speech data set. Why? Because it's almost 1,000 hours of audio and more than 2,400 speakers. So we took the audio only from that data set and passed it on to xADA, who is the teacher. However, on this first experiment, we didn't consider the blinks, nor the head motion, nor the motion, and got all the solves for those audio files, right, that come from liver speech, and store them into our synthetic data set, which will serve for training stADA. And that's how we trained it. And then when we compare, like, how much did we distill xADA into stADA? Well, on running time, when we're running this on a CPU per second of audio, xADA takes 172 milliseconds per frame, you could say, or per second of audio, while stADA is only 16 milliseconds. And the main reason is because Whisper, right? Whisper tends to be quite large, and we're here just taking the first few layers. Then when we go into the realm of number of parameters that the networks have, xADA has 103.5 million parameters, while stADA is almost 20 times smaller with 4.3 million parameters, which then this reflects on the space on disk that they take. xADA, and this is just the face component, would take 394.8 megabytes, while stADA is only 18 megabytes. So this could be deployable into mobile devices with no issue. And here is a video comparing xADA on the left and stADA on the right. And you will notice that xADA can capture the subtleties of speech. However, stADA gathers like the coarse, overall coarse animation of the speech.
At one end stood a great fireplace, in which a blue log was blazing with a blue flame, and over the fire hung 4 kettles in a row, all bubbling and steaming at a great rate.
Glue the sheet to the dark blue background. It's easy to tell the depth of a well.
Cool. And now let me show you a demo of how it runs in the engine. So for this, the first thing that you need to do is to install LiveLink and add the microphone. In this case, we've got LiveLink already set up, and you need to add a source. Then from the source, you go into the MetaHuman audio, go into the new created source, and then select the audio device. We're going to select this microphone over here. And then we'll call it subject name. Let's call it the cell mic. It's me. And once this is on green, this is ready to go. Then we select the MetaHuman that we want to look at. So this will be Orlando. And then we go into the details. Within the details, you just need to select the LiveLink subject that we just created, which is cell mic, and then just link it with use LiveLink. And there we go. Hey, everybody. Thanks for coming. All right, and that's it from my part. I'll hand it off to Sarah.
So yeah, just to summarize and to wrap things up, we have presented xADA, expressive audio-driven animation on MetaHumans. And this is a method for animating the face, tongue, and head of a MetaHuman from speech. We've talked you through the R&D behind this, so our data capture, our model training, and we showed you a brief demonstration in MetaHuman Animator. And Salvador has talked through the streaming audio-driven animation solution, which is currently in beta. And he's talked about how it was trained using a teacher-student paradigm, and he demonstrated this in MetaHuman Animator as well. So this wraps up our talk. I would like to invite you to the booth to test out both of these versions if you are interested. And we also link to the documentation from that QR code there. And yeah, any feedback is very welcome, and thank you for your attention. Thank you.